does amyloid beta come from? It is a cleavage byproduct of amyloid precursor protein. So if I could direct your attention to the bottom right, this kind of illustrates it. When amyloid precursor protein is cleaved or snipped, cut, whatever you want to call it, it floats around and it aggregates together, and I'll explain in the next slide. But there are there are a few main types of amyloid beta, but the one that my lab or I focused on was amyloid beta 42. So what is aggregation? Aggregation of amyloid beta 42 is pretty much the coming together, the clumping of single peptides of amyloid beta, and then those monomers, what we would call single ones, would come together to create oligomers, and then those oligomers come together to create fibrils, and fibrils are a component of plaques, and plaques are present in the brains of Alzheimer's patients. So, recap, general pathway of Alzheimer's. First, amyloid precursor protein is cleaved, and it's what's produced is amyloid beta 42. Then aggregation occurs. So monomers, single peptides of amyloid beta 42 come together to create oligomers. The oligomers come together to create fibrils. Then fibrils come together to form, or a portion of them form plaques. And the reason these are not good is because plaques tend to surround neurons, and they can disrupt the normal cell function. And disrupting normal cell function can lead to. So, what did I do? I did purification. So, what is the importance of pure compounds, you may ask? Well, in our lab, we like to have at least a 95% purity for our compounds, because even in minor impurities can have an impact on your results. Also, if you didn't have pure compounds, you would need to know every single impurity and the effects of all those impurities, which is a lot more work than just having to purify them. So, how do we purify amyloid beta? So, quick overview of the methods. The two main ones I used was reverse phase HPLC and then mass spectrometry. Some other things we did was before or since the synthesis of the peptides amyloid beta 42 is stuck to a resin, we have to cleave it from the resin before we run it to the HPLC. Also, we also use the nanodrop to find the concentration, and then we also freeze dry them to store them for later use if we ever want. So, what is a reverse phase HPLC? Simply put, it's a way of separating by hydrophobicity. So, if I could put your attention to the right, that's the instrument, the HPLC. On the top is acetonitrile and water, pretty much. And that's called the mobile phase, which is what's constantly running through the instrument the whole time. It's also what is pulling the sample that you inject through the column and into the actual instrument. So, and then now to the left, these are the three columns I used. They're standard. The standard one that I used was for the first round of purification with the crude peptide. The second one I used was the semi-prep one, a little bit smaller. Well, kind of really smaller, but that's for the second round of purification. And then the third one I used was the analytical one, which was only for analyzing our sample. So, what is separation by hydrophobicity? So, inside of the column, this metal tube on the right, is a stationary phase, which is non-polar, kind of like silica gel. And what flows through it is the mobile phase again, and that's polar. So with these interactions, the compounds that are more polar or hydrophobic drain faster versus the stuff that's non-polar, they drain slower. So these are the 4 steps that I made up. So the first step, separate the crude peptide with HPLC, then analyze the fractions using mass spec. Then after that, we select the fractions that have strong amyloid beta 42 signal. Then finally, we purify and analyze with HPLC. So this is the first round of purification with the crude peptide. It varies from run to run, so I might not get all 4 of these peaks again if I do it with a different sample. But for this sample, I had 4 fractions, and each fraction was collected. Usually we would collect them from the beginning of the peak to the little bit before it starts going down. We do that for all 4, so we'd have 4 tubes, and then that would lead us into our next step, which is analyzing the fractions using mass spec. So each fraction would be analyzed, so there would be 4 different graphs. So what exactly is mass spec? Simply, it's a way of identifying a compound in our case, a peptide. And it's a very sensitive instrument, so there's going to be a lot of byproducts that you'll see, a lot of lines. And then the way you identify a compound with mass spec is it's identified by the mass to charge ratio. So a quick overview of how to look at a mass spec graph. So on the y-axis is the relative abundance or the amount of compound. So the higher a line is, the more of that compound is present in that sample. And for the mass to charge ratio, it's exactly what it sounds like. Mass, so the mass divided by the charge. So the more mass a compound or a fragment has, the more along the right it'll be, or more along the x-axis it'll be. So there's that. Now that we know what a graph looks like, we can select the fractions that have strong amyloid beta 42 state. So I'll just tell you, fractions 1 and 2 have high concentrations of byproducts, which is not what we want. And they both also have low signal amyloid beta 42, which is also not what we want. Fractions 3 and 4 have a low concentration of byproducts. We want that. And they also have a strong signal of amyloid beta 42. Great. So how do we select these fractions? We need to know the mass of the amyloid beta 42, which is 4,514 kilodaltons, and the net charge of the whole thing, which is positive 4. And then there's some other stuff that because it was dissolved in acidic conditions, but I don't want to worry about that. So we have this mass to charge ratio of 1,129.5, which is around what we want to look for in the graph. We want the highest point or the highest line to be 1,125. So these are the two fractions that were bad. Fraction 1, as you can see, maybe not. I'll just tell you, 965 at the very top. That is something else, and we don't want that, so we throw this out. Fraction 2, 332. It is also not what we want. And also you can see there is 1129 in here, but it is super low. So we would also not use this fraction either. But for fraction 3 and 4, I have fraction 3 right here. It's 1,129 is the highest peak. It's really high, so it's great. And also the byproducts are, there's a relatively low concentration of byproducts for this one and also fraction 4. So fraction 4 also has, can't see it, but also has 1,129. So great. So now we use fraction 3 and 4 for the final step, which is purifying and analyzing HPLC. So we would use the semi-prep column, which is a smaller column. I don't exactly know the exact diameter, but it's much smaller than the first one. So the way we would collect it is you can see there's a peak right here. We wouldn't collect this one at all. It's just some background noise. But right here, there is a little bump right here. We would want to collect after that. So I'd mark them where you want to collect. We want to collect from here to here to get the best purity. That's what I'm told. So the next thing we would do, the final thing we would do, is we would analyze the amount of amyloid beta inside of our sample. And then that's how we get purified amyloid beta 42. So what we would use for the purified amyloid beta 42 is they run a THT assay. They do some biological work. And my mentor also wants to get a transmission electron microscope image of amyloid beta 42. And then finally, he wants to compare the properties of amyloid beta 42 and N27 derivative amyloid beta 42. So I would just like to thank the Raskatov lab, Evgeny Raskatov, my PI, Pachan, my mentor, Kayleen, Gaby, and my liaison, Bradley Stone, and then everyone from Access, and of course, the NIH.
Thank you.